Thanks for watching another one of our seminars. Today we're talking about zoning cast iron boilers with circulators, and it can create problems. I'm not going to sway one way or the other. I don't care if you zone with zone valves or you zone with circulators. End result's about the same. There's some arguments that work to both sides. But today we're talking about cast iron boilers and zoning with circulators and the problems that we can be creating. When we're zoning with circulators, we want to make sure that we size the boiler properly. Always, always, always. Use a heat loss or some other good method, not a rule of thumb method, but a good method. Some people can calculate off of fuel usage. Does it work? Yeah. I'm a little concerned when you have like a gas boiler and you're trying to do it with gas and you're trying to determine what the gas usage is for heating, but you got a gas water heater, gas dryer, gas stove. It's really hard to calculate that out. Some people do it with oil and degree days, but how much oil is still in the tank? How much is in the tank when it started? So, and even with a manual J heat loss, which is what we do, there's some flaws there because it's about 20% heavy because it calculates wind blowing against all four walls at the same time. There's nowhere in the United States I think that happens. And if I'm wrong, let me know down below. So properly size the boiler. Size the piping headers properly. There's a misconception that because there's a certain size hole in something, that's the size pipe you put in. That really isn't true. If you get into high efficiency boilers, sometimes the piping coming out of the boiler should be larger than what the boiler tapping is. And with cast iron boilers, a lot of times it can be smaller because it has the same size tapping through the whole product line from maybe 35 or 40,000 BTUs up to 299,000 BTUs. They're going to have the same size tapping. You don't always need that tapping inch and a quarter, inch and a half, depending on your heat loss. And the headers, size those headers properly. There's quick, easy ways to do it. We can show you that on our tabs on our website, Comfort-Calc.com. And third, watch your delta T's. Cast iron boilers work best between 20 and 40 degree delta T. So we're going to tell you how to figure that out, and then we're going to give you a little bit of an easy way to get to it. But we have to know what our flow rates are in the zones. And that's where the heat loss comes in. Do the heat loss, do it per room, break it down into zones so we know what we need in those zones. I'm going to talk here about existing cast iron boiler and just figuring out what our flow rates need to be. Hopefully we have a flow restrictor of some type on the piping so we can get it where it needs to have the proper flow rate for that zone. The delta T we can measure. We can measure delta T and figure that out pretty easy. The gallons per minute is what we need to know going through the boiler, what the minimum maximum is. We have to have that information. The BTU, that's the input of the boiler. We could also calculate the BTU output of radiation if you want, but right now we're concerned with the boiler. And then the flow rate affects your sizing of your circulators. So not one circulator is a one size fits all. You say, well, I got auto adapt. Yeah, well, it's not magic. You still have to set it up. So let's walk through this and determine our flow rates and what's happening with the boiler. Let's just assume each zone is 3 gallons a minute. We're just going to keep it simple. Very seldom would they all be the same, but there's 6 zones on this boiler. The boiler is 100,000 BTU input. So if one zone's running, we're going to have 3 gallons a minute flowing through that loop and then through the boiler. You'll be getting the 3 gallons a minute. But if all 6 circulators are running, we're going to move 18 gallons a minute, which means that we've got 3 gallons going through each zone, and then we're going to have a total in the manifold piping of 18 gallons a minute. So is that pipe, that header sized for 18 gallons a minute? So if that one circulator is running at 3 gallons a minute, my guess is it's not going to be enough flow in the boiler. and we're going to short cycle that boiler to death. So when we're short cycling the boiler, we're reducing the efficiency on the boiler. We're putting more wear and tear on the boiler. We want it to stay running longer. But when we're moving all 6 zones, because all 6 circulators are running, now our flow is probably going to be in excess of what the boiler can handle. And what happens there is the boiler can condense for a longer period of time, or maybe condense the whole time. Now, are all 6 zones running all the time? No. They'll overlap. And the more flow we get through the boiler above what it can handle, the longer it takes to get the water temperature up to the desired temperature above condensing. Think about the time when all 6 circulators are probably going to be running at the same time. We experienced this back in December of 2022. We had those frigid cold weather, that frigid cold weather before Christmas. And probably a lot of times you had 5 or 6 circulators running at the same time, putting more flow through the boiler than the boiler could actually handle. Therefore, it really struggled to get water temperature up. And it probably didn't get it up until you started dropping out some of the circulators. So the idea is get the temperature where it needs to be in a reasonable amount of time, stop the condensation, and get those zones heated. So if we talk about the hydronic formula, there's actually 3 formulas that make up the hydronic formula. And one of them is calculating the delta T. What's the delta T? Well, it's easier to measure it, and that's normally how we figure that one out. And then the second one is the BTU output or input through the boiler. If there's no sticker on the boiler, you can calculate the BTU input knowing some other factors. So we can read the sticker if it's there. If you want to calculate the flow through a zone, and I've done that on job sites already because it wasn't heating right. And usually they were radiant in floor systems, so I could see what the delta T was, and if it was way too wide, of course the beginning part of the floor is going to be warmer than the ending part of the floor. So that's where you could use something like that. And the flow, gallon per minute flow, through the zone or through the boiler, through all the zones and through the boiler. So this is where we apply hydraulic formulas, and they're really easy formulas to do. I was a contractor for 20 years. Then I worked for the manufacturer for 25 years. And when I was going to seminars as a contractor, the last thing I wanted to do was sit in a seminar where they had formulas. Well, today we're doing formulas. So we did learn the hydronic formula a long time ago, and that formula has helped through the years on resolving some problem jobs. It's amazing how many times somebody says, I got an area that doesn't heat right. And you say, well, okay, what's the flow in that area? I don't know. What's a delta T? I don't know. Well, you need those bits of information to figure out if we're moving enough water. So, or we need hotter water maybe. Sometimes somebody says, just turn the temperature up. Well, maybe it's not the temperature. Maybe it's a flow issue. If the more water you flow through a zone, the more heat you get out of it. Now, the more water you flow through the zone, it's a possibility you get less temperature though. So you kind of have to know what these facts are before you get too involved in it. So it's easy to figure out. So we're going to look at flow. So we have F equals Q divided by 500 times dt. So F is flow. That's what we're trying to find out. Q is your BTU input from the boiler, the DOE rating. On gas, it's the middle rating. On oil, it's the first rating. So we can get Q, the input, pretty easy off the tag on the boiler. And the last one is dt, delta T. This is the difference between supply and return piping. Just measure those temperatures and do the math. Just take your supply temperature, deduct the return temperature, and that's your delta T. Okay, we're going to calculate flow. We can do this on a zone by looking at the supply water temperature to that zone, return water temperature from that zone, and have the circulator running. We're going to look more at the calculation for flow through the boiler. Because if this boiler fails, we want to know why it's failed, why it's leaking, why it's all rusted up inside. So we're going to assume that all these 6 circulators move 3 gallons a minute. That's not common in a standard application. They don't move the same amount of water. So we would have to determine the flow through the zones if we want to do a zone. But again, we're looking at the boiler. Turn the thermostats all up, get all the pumps running, and then let the boiler run for a while and do its the delta T. That means we're going to measure supply water temperature and we're going to deduct the temperature of the return off of that. So we're going to have it, in this case, 11.1 degrees difference between supply and return. To do this formula and calculate flow, we have to know the input of the boiler. On a gas boiler, it is the middle number. The DOE output number is the middle. You have your input number, your DOE output, and then your net. On oil, it's the first number. It's the higher of the two. That information off the label, and we find out this boiler is 100,000 BTU input, which is DOE input. Next, we have to do what's in the parentheses first. We take the 500 times 11.1. That's the constant for water. If you add antifreeze, you have to find out from the antifreeze manufacturer what their constant is for determining flow. They'll give you that. But for just water, we're going to use that as 500. So now we take 500 times 11.1, and that comes out to 5,550. And then we take 100,000 divided by 5,550, and it comes out to 18 gallons a minute. And that's what we would have if we had 3 gallons in all the zones, which we don't in most cases. So we wouldn't have known that up front. I just gave you that information going in just so you could kind of put the two together. So this boiler is a 100,000 BTU boiler. We want to work between 20 and 40 degree delta T's. So we are moving way too much water. The water's not heating up quick enough. The boiler's condensing longer than it has to. And when all these zones are running, when you have to depend on them on the coldest days out of the year, that's when most of your zones are going to be running, you are not heat to the house quick enough. And your thermostat will never be met. And it may not be met in any of the zones. It may meet in some of the zones that are smaller, but it may not. So it would depend on the piping, the size of the circulator, the size of the boiler. But if you have zones that aren't heating, it is normally a delta T or flow issue.
We discussed 20 degree delta T's, how to get 20 degree delta T's. It's pretty simple. You divide the DOE output of the boiler by 10,000. So we have a 100,000 BTU boiler. We divide it by 10,000. That gives us a 10 gallon per minute flow rate. So how do we get a 40 degree delta T? You just divide it by 2. At that point, you divide it by 2. So 100,000 BTU boiler divided by 10,000 is 10 gallons a minute. Half of 10 gallons a minute equals 5 gallons a minute. So that's your 40 degree delta T. You're going to cut your flow rate from a 20 degree in half to get a 40 degree delta T.
We use the same drawing that we used in the last slide. So we have 6 circulators, 3 gallons per zone for each circulator, and therefore we have 18 gallon total flow through the boiler when everything's running. Our pipes are sized properly for our flow rates. That's actually a different seminar that we have on our website, pipe sizing, and that we're at comfort-calc.com. So it's a mild day, 2 circulators are running. We're going to be moving about 6 gallons a minute. The boiler can handle 10 gallons a minute. It's inputting enough fuel to heat the flow rate of 10 gallons a minute. It's going to go out at 20 degrees higher. If we're moving 6 gallons a minute, it's coming in at a certain temperature, and we're going to raise it more than 20 degrees when it goes out. And then let's say it continues to get colder, and now we bump it up and we have 4 thermostats or 4 zones calling. And now if we take 4 times the 3 gallons per minute, that's 12 gallons a minute. We're flowing 2 gallons more through that boiler than the maximum flow rate that boiler is rated at a 20 degree delta T. So we're not going to pick up 20 degrees anymore. We're going to pick up something less than 20 degrees. So here's where we start getting into problems. We're going to still send 100,000 BTUs out, but they're going to be distributed between more gallons. So therefore, we're not going to have as much temperature rise. And it's going to take longer to heat the zones. It's going to condense more, bad for the boiler. So we're not going to short cycle like we would with 6 gallons a minute. Now we've doubled the flow, and what happens now is it's going through faster. More water is going through that boiler, less time in the boiler. So this creates problems with the short cycling, creates lower efficiencies, higher maintenance. It's harder on the equipment. So if all 6 circulators come on, now we're moving that at 18 gallons a minute. Now we're 8 gallons above the maximum flow rate of the boiler. We're almost double. There's a couple of ways to handle this situation. The best way, in my idea, is what we call primary secondary piping. Primary secondary piping in itself does not protect the boiler from condensing. We want to clear this up because a lot of people think it does. It does not protect the boiler from condensing. If you want to see ways of protecting a boiler from condensing due to lower water temperatures, go to our website, go to cast iron boiler tab, and you will see a lot of ways of protecting a cast iron boiler. But I think in this situation, we can protect the boiler easily with primary secondary piping. And we'll explain why in the next slide. Here's how we can fix this. If there's a cast iron boiler and you have these flow rate issues where you have too much water flowing through the boiler, we can do primary secondary piping, and we can add a circulator to the boiler. Now we'd add that circulator to the boiler, it's going to flow water just through the boiler. It's going to pull it down from the system piping, it's going to put it back up to the system piping, and then the system circulators are still going to flow all the water they need to flow depending on how many circulators are running. When we get these T's in the system, we want to get them as close as we can. I know they look a little far apart here, but if you can get those T's just about touching, you'll create better hydraulic separation. Now when we get these two different flow rates, we get all these pumps running up in the system and we got that boiler pump running. It doesn't matter if one's higher and one's lower than the other, because hydraulic separation, closely spaced T's, we will not affect the flow of one circulator to the flow of other circulators. So the boiler can run at its flow rate, the system can run at its flow rate, and they will not affect each other's operation. Therefore, the boiler can run at a different delta T. If we slow the flow of the boiler down to get the water hotter as it goes through the boiler so it stays in the boiler longer, it will not be affected by all the flow rate in the system. And normally in North America, we design around a 20-degree delta T for standard radiation. If we go to in-floor radiation, then we're going to use a different delta T in the system. But it doesn't affect the boiler delta T because that holds the same. So if we just follow the rules of primary, secondary, and make sure all of our pipe sizing is correct, we will have a long boiler operation. A lot of you are using high efficiency boilers today. Condensation with those boilers is not an issue. Delta T is still an issue. We'd like to push maybe the delta T a little bit higher than 20 degrees in the boiler with a high efficiency boiler. We may want to go 25 or 30 degree delta T. In the system, it's not going to change what the boiler does because of that closely spaced T's. Now, with primary, secondary, there are other ways of creating the hydraulic separation without using closely spaced T's. There's buffer tanks, there's hydraulic separators. We can look at those again on our website in a different seminar at Comfort-Calc.com. Thanks for watching this preview to the end. If you found this informative, please like and subscribe for us, help others to find us, and just slam down that like button. Builds the algorithms for our new site. Thank you.